after 17 years of training, I came to DANFOSS. When I first came to DANFOSS, I was Director of Business Development and Market Research for TurboCore, and we figured out, closer to the mic. I figured out in that developing the business of those compressors that the best way to develop the business of those compressors was to focus on the systems, not to focus on the compressors themselves. And so we took that concept and started to expand on it to say, okay, if we could develop a full system, portfolio of system solutions to enable what we call rapid electrification retrofits, what would that look like? So we kind of developed a concept from there and basically developed a business based on that. And that's what my team does now. I'm officially the Director of Industrial Energy System Solutions is the title now. But what we work on is large-scale integrated energy system designs and retrofits. And what I'm going to tell you about is our experience and learnings from that over the last few years. So that was about 5 years ago when we started to make that transition. About 3 years ago, my wife and I shut down our 800 square meter Colorado home, sold our 3 cars, our son went off to college, and we moved to Denmark. And so I've been there ever since then, working on this concept, working on this system, or working on this business, let's call it. So what you start with, if you're going to do large-scale integrated system designs, what's the primary driver? Why are we focused on this market? The reason is because there's such a significant opportunity based on energy recovery. There's various versions of this. You've probably seen a couple of them before. But us as engineers, we like I said, I'm going to nerd out a little bit. We like Sankey diagrams, and this is the best one that I've seen to show how much energy from primary energy generation to final energy use is being wasted. They all say roughly the same thing, that when you get down to that final energy use, it's about 2/3 of the energy that's being wasted. And so what we're trying to do is show on the large scale, not just individual houses, individual homes, electrification, etc., but on large scale energy systems, how do you do that? And do it in as simple a manner as possible. Basically, make it as easy as if you were just going to electrify your home, replace your boiler, and utilize a heat pump. When you do this, you have to have, our experience is, you have to have 2 baselines. So you have to have first of all, you have to have a business case if you're going to electrify. If you're going to replace a boiler and with a heat pump, whether it's on an individual home or recovering heat from a data center to go to a district energy system, you always have to have a business case. In our experience, you have 2 business cases. One of them is what you're replacing. 95% of the time, that's a condensing boiler or a boiler. And then you're also comparing it to, or doing the business case versus the next best alternative to do the exact same thing. And usually, that's an air-to-water heat pump. What we're trying to do, about 95%, but our projects are with water-to-water heat pumps. So as opposed to an air-to-water, you're in general recovering heat from the air, right? You're pulling heat from the air in an air-to-water heat pump. A water-to-water heat pump is taking heat. When you electrify heating, the first thing that you realize is everything is now just moving heat. Cooling is moving heat, heating is moving heat. All you're doing is moving heat from point A, where it's not needed, i.e. cooling, to point B, where it is needed, i.e. heating. And it's just a matter of how much energy you have to expend to move it from point A to point B, and then upgrade it to the energy usage level that you need it at. And so if you're doing that, your baseline, that second baseline, becomes an air-to-water heat pump. Because in general, an air-to-water heat pump is going to operate at about 2.5 to 3.5 COP. That becomes your baseline for what you can increase that efficiency level to create that business case. And in general, what you see with the heat pump, who can, quick show of hands, who understands why a heat pump is significantly more efficient than a boiler? Anybody? Okay. Yeah, I think most people in this room are going to understand it. Basically, anytime you're converting energy, your maximum COP is 1, right? You have laws that prevent you from, when you're converting energy, to having a COP or coefficient of performance greater than 1. If you're moving heat, back to that point, if you're just moving heat and boosting heat, you're not held to the same laws as far as what level of performance you can get to, right? And so that's why, you know, when you're replacing a boiler and you're comparing it to an air-to-water heat pump as the next best alternative, first of all, the heat pump, whether it's an air-cooled or an air-to-water or a water-to-water, is going to be significantly more efficient because you're no longer converting energy. And the efficiency increases as you go from full load down to part load. And the goal, ultimately, what you're trying to do is exceed spark spread. Quick show of hands again. Who is familiar with the term spark spread? Anybody heard that? It's also called energy cost ratio. It is the #1 factor that governs whether or not the business case pencils out to do a heating electrification retrofit. It's the cost ratio of electricity to gas. So kWh of electricity versus kWh of gas. There's various terms for it. The one that caught me, because ultimately I'm an engineer, but I'm a marketing guy too, is spark spread, because it's kind of catchy, right? But that, ultimately, your goal is to exceed that. Electricity, as a general rule, except for Sweden, is always over the price of gas for a kWh. And your level that you can increase over that, or the ratio of increase of the efficiency of the heat pump system versus that spark spread, is going to govern the payback. Govern the payback versus that fossil fuel fired boiler that you're replacing. So this is a spark spread across Europe. And of course, what you see in Greece is you're a little bit less challenged than most countries. You're about the same as we are in Denmark. Your spark spread ratio, or energy cost ratio, is about 1.5 to 2.5. That becomes your baseline. You have to have a heat pump system that's over that to have a payback versus the fossil fired boiler that you're replacing. That becomes your baseline. Then you just work up from there. So why is a water-to-water heat pump system where you're recovering heat from something so much more efficient? Again, because you're recovering heat from something. Air is a fantastic source, but if you, especially here in Greece, but if you go up to Denmark and you go into the middle of the winter, air becomes not such a great source, and especially when you need it most, right? And so that's what you're challenged with, is the performance during that period. If, as opposed to that, you can recover heat from a process that's being rejected through cooling towers, to bypass it through a water-to-water heat pump, to supply, to replace the boiler, to electrify the heating system, it is going to be significantly more efficient, because what you did is just decrease the work that that heat pump has to do, as opposed to an air-to-water heat pump that's recovering the heat from the air. And this is based on an actual system that's being commissioned next week and at a metals forming company manufacturing facility in Denmark, in southern Denmark. But this is the actual performance of that system too. So the cooling system, which is supplying this, 16 degrees C, I think? Yeah, 16 degrees C. The cooling system, which is supplying it back to the cooling tower, and then that then goes through a heat exchanger to supply it back to the treatment tanks, is provided at about 3.4 COP. The heating system, you're replacing that fossil fuel fired boiler at about 0.95 COP, is about 4.6 COP on just the heating, and what we call the symbiosis efficiency. This is the thing, right? This is the thing that doesn't hit most people when you first look at these numbers, because everybody, we're all of the mindset that if you have a cooling system and a heating system, you have two separate levels of performance, and they're all provided by two different systems, right? That's the way we think. That's the way we've been trained to think about these systems. But if you're going to do a piece of equipment that does both, provides the cooling, again, because you're only moving heat from point A to point B, then it's the level of performance of both of that, both of those factors, providing the cooling and providing that heating, that are critical. When you combine those together, you're ultimately getting the capacity of both. The cooling, whether it's an industrial process or a data center or a hospital or whatever it is, and then the heating, whether that's again, those different options, and then going to district energy, But you're getting, the point is, you're getting the performance of both, again, on one piece of equipment. So that then drives you to combine the performance calculation for both of them. This is why it's critical. So this is what I was speaking to earlier. These are the first, when we started doing this, we started tracking all of the projects that we worked on. Don't try to read the chart, just remember 2 lines. This is going up in differential, and this is going down in efficiency. So this was the first about 160 projects that we worked on, doing concept designs for, and it shows the efficiency versus the differential of all of those projects. Here's the summary. So every 1K that you go down in the work that a heat pump has to do, you're going up in about 2% in heat pump efficiency, and that's direct inverse correlation to operating costs. This is the main point, right? Back to the business case. If you want to have a payback, the less work that a heat pump has to do, the quicker the payback is going to be. You have 2 different levers for that. It's increasing the source or decreasing the demand. Both of those are valid, right? When you talk about data centers, and you're moving from traditional air-cooled to liquid-cooled data centers, what does that do? Right? I think there's going to be people in here who have experience with the new high-performance computing data center designs. I've been in the industry for 30 years. Everything that has changed about data center cooling systems can be summarized in 2 factors. Getting closer to the CPU and going up in cooling temperature. Everything else is just details. All of it, every technology, every move in terms of data centers is driving to one of those 2 things, or both, right? And so when you go from air-cooled to liquid-cooled, which is what a high-performance computing, AI, whatever you want to call it, data center is, the reason you're going to liquid-cooled is because you're generating so much heat that you can't reject it with air anymore. That non-dense fluid can no longer reject all the heat from that. But if you're going to go to liquid-cooled, direct on chip over top of that GPU or CPU server, then you can't do that at traditional cooling temperatures. Because what's going to happen, you're going to condense over top of it, which condensing water over top of a server tends to be a little bit of a disastrous scenario. And so you push up the temperature, also because you don't need to reject that heat out as much anymore, because you can do it because you're right over top of the server. So that pushes up that temperature about 20K. This is one of the things I was talking about. We talked about water usage in an earlier presentation. That struck me. When you go from a traditional air-cooled data center to a liquid-cooled data center, everybody's talking about the water usage. And the people who really know data center cooling systems just kind of laugh, because the future data center doesn't use any water. Why doesn't it use any water? Because you just pushed up the cooling temperature by about 20 to 30K because of that direct on-chip liquid cooling, which means no longer are you going to need that chiller or that cooling tower necessarily. This is a not foregone conclusion, but you're pushing up that cooling temperature, so you no longer need the cooling water to go into the cooling tower to reject that heat anymore. So the primary usage of water. Anyway, that's kind of a sideline, but that's another factor that comes into play when we talk about this. So this is an example. If you have a 40K delta T from a data center, for example, with liquid cooling at about 35 C on the cooling side, that's what most of them are being designed for. And then you're rejecting that to about 75 C for a district energy system, that's about 40K of work, and that comes out to about a 5.5 COP. As opposed to that, if you're getting it from, for example, seawater in Aalborg, Denmark, this is a literal example, to then also go to a district energy system, but doing about 70K of work from that source to that demand, you're at about a 3.2 COP. The reason we did this is because when we go in to do these integrated, how long am I? Okay. When we go in to have these first conversations, these engagements to do these integrated system designs, we want to be able to tell them before we leave that first conversation. If they can tell us the temperatures, we can tell them roughly whether or not they have a business case for the project. That was the goal, right? So that's what we're working towards when we're doing these calculations, these charts. The other point that we make is everything is connected. So if you're talking about the energy transition, you know, we talk about data centers, we talk about climate change. I've heard a lot of conversation about renewables integration, electrification, what we call sector coupling, that's what we used to call our theme. And the criticality of that to resiliency of energy systems and storage and microgrids and district energy, and then demand response, the implications for that, and demand side storage. This is primarily what I'm focused on in this presentation. But the whole point is when you talk about the energy transition, everything is interconnected. If it's not interconnected, then it's not a factor that's going to last, right? Everything, you can see a flow down from first level macro trend down to the demand side, and then ultimately to what my colleagues like is the component implications, what we need to work on next in terms of components. But you can see a flow down, you can see a trend of what's driving what's needed from a technology standpoint and systems. So these are a few examples. Again, every time we work on a system like this, we try to summarize it based on source, demand, and then heat pump. When you go into a project, when you're doing evaluation of whether or not it's going to make sense to recover heat from an industrial process, to replace the boilers that are heating that facility, again, the source temperature and demand temperature and capacity and simultaneous operation are what are most critical to that payback, to that analysis of whether or not that retrofit's going to make sense. When we do this, we try to summarize it in a simple way and say, here's your source, here's your demand, and then ultimately meet in the middle. You start on the outside, you meet in the middle to say what is the best choice as far as the technology to use for the heat pump to meet the requirements of that source and demand and differential and that capacity. These are a few that we worked on. You'll see several different, but you start to summarize them in terms of the source and demand temperatures, right? It tells you a lot. You know, what is your optimal source? Your optimal source is going to be your higher temp, but you know, some of these are not necessarily going to be available that often. These are much more commonly available. And then on the demand side, what you try to target is also operating temperature profile changes to those systems. You know, in district energy, I've had a couple conversations about district energy in the last day. The trend that's happened in the last 30 years in Denmark is to lower down district energy temperatures, but they can do it at about 1 K per year. If you have a district energy system, you got to change out radiators to fan coils to underfloor, do all of those changes that lower down the temperature requirements that then drive ultimately the lowering temperature of the district energy system itself. It takes a long time if it's an existing system. And so when we have these conversations, one of the first ones that we have is, can we also explore the end devices, both on the cooling side and the heating side, to change the operating temperature profile, to make ultimately this decision as the last decision to then drive the most efficient system. Oops. There we go. It's kind of sticky. There we go. This is one of the first ones that we worked on. This is a heat recovery from our own data center at our headquarters. This is right across from my office in Nordborg, Denmark, where we wanted to go in and say, okay, if everything's, the other thing that we look for is everything hydronic. If the heating's hydronic and the cooling's hydronic, then you've got a relatively simple retrofit to tie those two together. And we focus on critical facilities. If you focus on critical facilities, data centers, hospitals, industrial facilities, wastewater facilities, you're almost always going to have simultaneous operation of the availability of that heat and then the use of that heat at the same time. And so what we try to point out is, back on the hydronic system, if it is hydronic, then it's really easy to tie in to recover that heat, because all we do is tie into the cooling return line to take that and bypass it through a water-to-water heat pump that then boosts it up to replace the energy going into the campus energy system. So it becomes a very simple retrofit. You're not replacing anything, you're just adding to it. That then provides the base load cooling for the data center system. Those existing chillers that were there, and this is based on an actual use case, the existing chillers were installed about 7 years ago. This retrofit was done about 4 years ago. And these are still there, but they just act as backup. operating basically like the backup power system, operating maybe 5% of the time a year. Anytime we're not recovering enough heat for this to drive enough cooling to cover the cooling of the data center itself. This is another example we saw in a hospital earlier. This hospital that we looked at in Germany had a 6 megawatt district cooling system and a 38 megawatt district heating system. And so we were looking at what can you do to make a more integrated, or electrify, first of all, replace some of that CHP plant, some of the capacity of that CHP plant up here, and then ultimately create a more efficient system with a good payback. So this was the retrofit. What you want to do is, one of the other points we make is close the loop. What do we mean by that? Like if you're not rejecting heat through cooling towers and dry coolers, that's the first thing we look for. If a facility, a critical facility has cooling towers, there's your target. That's your source, right? No energy should be rejected in the future if you have heating load at the same facility, right? So you don't need those cooling towers anymore, or you just have them as backup. And you don't need those dry coolers anymore, or you just have them as backup. But in this case, we said, okay, close the loop. And what we meant by that is replace that cooling tower with a dry cooler, boost it up a little more, because you're going to use, this is your base load heating, right? That 8 megawatts is your base load heating. So if you're recovering heat all the time, it doesn't matter if you're recovering it at a higher temperature, right? Because ultimately you boost it up with that second stage to then supply the district energy system, campus energy system. This is a more complicated one. Don't try to take all of this away. This is a little case that we worked on in Copenhagen. August, I'll show you if he's in here. I'll show him when he comes to Copenhagen if he wants. But this is a multifamily brownfield redevelopment where they were adding a supermarket and base floor on the 2 base floors. I got it. Huh?
3 more minutes.
3? Okay. I got to jump ahead. But the point was, we're integrating multiple systems here. You're integrating an ADIS, aquathermal energy storage system, that takes the heat from the ground to provide the cooling to the supermarket, and then ultimately to these buildings, and then recover that heat through the heat pump to supply to the heating of those same residences, and then also to supply to the air handling units for the supermarkets. But what you're doing ultimately is tying in multiple systems together. So the other point is, it's not just one at a time, right? And for a source and demand, you can tie multiple together if you can create that energy balance with them. And so this is one of the last examples that I'm going to go through. This is an industrial process that we worked on. This is that same metals forming facility. This is the one that's being commissioned next week. So I'm just going to highlight some of the details here. So when we went there, we sat down with them and we talked about embodied carbon earlier. We asked these, when we work on these projects, the thing that we learned the hard way is that we need to get in first. Before anybody even knows what the project is, we need to have that conversation with the customer. Right? We don't want to react. It's much better to work from a initial conversation to a concept design, to a detailed design, to a project execution in a straight linear path than it is to react to a disjointed process, a plan and spec process, right? And so what we try to do is have this initial engagement to say, what is the opportunity? And what they told us was they had too much embodied carbon in the final product that they were delivering to their electric car company customers. That drove us to say, where are you still using gas? They said, right here, and that's it. Everything else at this facility was electrified. They said, we're only using gas to heat the facility. We said, okay, so you have these metal billets that you're heating up to 500 degrees C, that you're then running through this parts cooling tank after it's formed into those parts. And then what are you doing with that heat? And they said, rejecting it through cooling towers. So, okay, we know exactly what the project is. It's just working out the details now to tie these 2 systems together. That's what, that conversation was almost exactly 2 years ago, a little over. And we're finally executing the system. So they still take time, but it was a linear process. It just had some delays in there. But ultimately, what that drives, and I don't know if you guys caught this, I had never heard that before. That we've been waiting for CO2 emissions and the financial business case to ultimately come together. This was the first case I had ran into, and that was 2 years ago, where that was the case. And it's happened a couple times since then, where those two are coming together. That's fantastic news. When we do a business case now, I'm going to skip over this one. This is another one we're working on. It looks like this, right? Something like this. The other point that we make, you're not just replacing gas. Again, you're replacing the cooling, right? So the cooling that you're replacing at that facility, this is the gas savings. And this is for another facility that we're working on right now. This one's in Poland. A very similar process, cooling the metal presses and welding lines of this manufacturing plant to then recover the heat to replace the facility and process heat. So this same manufacturing process they have, and this is a universal thing when you're manufacturing goods, consumer goods. You have a parts treatment tank that you run all these parts through before you paint them to assemble them into the final product, if it's a metal part, right? And when you do that, you're heating it up to like 60 degrees C. That's a perfect target for recovery from cooling to replace the heat. And so that's what we did. And so that's what you see here. You see the gas savings based on the heating up of that parts treatment tank, and then also the heating of the facility. And then you have the chiller electricity savings, because you're replacing that chiller that was cooling those welding lines and cooling those the hydraulic presses, and replacing that cooling at the same time. So it's all the same energy that you're moving. So you count for that, and then this, right? And this is what I was just speaking to. This is the emissions reduction cost offset. This is the ETS. This is based on the actual emissions of the natural gas from that facility and replacing that. The CO2 emissions reduction, and then the resulting tax reduction. And then the dry cooler, they also have dry coolers on the roof that we're generating. Then you subtract off the electricity of the heat pump usage, straight line depreciation, heat pump maintenance, and it gives you a very attractive payback. That's before incentives. After incentives, it was about 2 years on the payback. And that's at an energy cost ratio of 2.4. Remember. So this system is about 5.5 COP, and that's what the goal is to double that. If we can double spark spread, back to that, what I was mentioning earlier, almost always we can have a 3 year or less payback with the incentives. This is a more complicated, I'm going to skip over this one because I'm out of time, right? All right, so heat pump efficiency, just to mention though, we took the opportunity, so air side recovery is a fantastic opportunity. There's so much high heat rejection that is being done. You know, everything is optimal when it's in water. Water is the ultimate energy transport mechanism. But if you can recover heat from air and do it in a solution that is self-powered to move that heat from point A to point B, then that is the ultimate solution. That's what we're trying to create here, is a thermal electric generator-driven hydronic microtunnel base module to recover heat and power the system itself to then add processed moisture to that, heated processed moisture to that same facility. Same process. Very interesting system, but it's still in process. Okay, so as takeaways, heat pump efficiency with heat recovery and renewables integration presents a decarbonization opportunity and attractive payback. That's the thing, right? When you talk about electrification, a lot of people default to, oh no, it's going to be a bad payback. That is not the case when you're integrating systems together. It's almost always a very attractive payback. Cost ratio of electricity to gas is critical. That is true. It's true that it's going to be attractive payback in Greece or in Denmark. UK, less so, because they have the informal barriers of natural gas subsidies and electricity taxes that increase that spark spread ratio to the point where it's not as attractive anymore. Critical facilities present the optimal integrated system design opportunity. You're looking for high operating hours, basically operating all the time on both the cooling and heating system, and then also the temperatures. Optimal scenario is in early incline engagement. If you can get in to define the project, that's the optimal scenario. That's what we go for. Energy audit enables, and the energy audit is the best way to do that, right? If you can get in and do an energy audit, I was trained in doing energy audits 30 years ago before I went to professional career, I actually went full circle back to it. And I didn't have any idea that I was going to do that in the end. But it's been fun because I learned everything that I used everything that I learned over the last 30 years to then come back to energy audits and learn how to do systems differently than most people are doing, and what we see as a better way. And partners are critical. You got to have the right partners because nobody can do everything. Okay. Oops. I don't have a question.
We do have questions.
Okay.